This program is a presentation of UCTV for educational and non-commercial use only.
So I think that any time you give a talk, the title of which begins with the words, "the future of," you should approach it with a certain degree of trepidation. Predicting the future is a dangerous thing to try to do. Now, in my normal work, in the stuff that I work with on a day-to-day basis, I am used to working with instrumentation that looks like this. In order to prepare today's talk, however, I've had to familiarize myself with a different kind of instrumentation. And what I'm going to try to do today is gaze into my crystal ball a little bit and give you my sense of what the future of planetary exploration might hold. I will begin with stuff that I feel pretty confident about because it's going to happen soon, and the plans are well underway. And then as I get further and further into the talk, I'll wave my arms more and more, and you should all get more and more skeptical as I do that. I'm going to start with Spirit and Opportunity, with the Mars exploration rovers. As Imke mentioned, the rover Opportunity is still going strong, still doing good things. We landed way up here near Endurance Crater, drove 21 months to Victoria Crater, spent 2 years exploring there, and since then we've been striving to reach the rim of Endeavour Crater. This shows the route that we followed: landing site, Endurance, Victoria. Here's where we are today. There's the rim of Endeavour. Now this shows the rover's current location right there. We have wandered into a field of small impact craters, 4 of them. Their names are Faith 7, Sigma 7, Friendship 7, and Freedom 7, after 4 of the spacecraft that were used during Project Mercury. These pictures just came down today. This is from our current location, looking east at Freedom 7, looking west at the smaller crater of the 2, Friendship 7. You can see there's a very fresh craters. They're rough, they're rugged, they formed fairly recently. They haven't eroded away much. Now, it's about the future, so where are we going next? Where we're going next is the rim of Endeavour Crater. And the reason we've picked it, here's a picture from orbit that shows what the rim of Endeavour looks like. The really interesting thing on this slide, though, is that wiggly black curve there. That wiggly black curve is an infrared spectrum obtained from orbit of the rocks on the rim of the crater. And what we've done here is match it up against 3 different curves of minerals that we've looked at in the laboratory, and you notice that these dips in the spectrum line up beautifully. These minerals are clays. These are clay minerals, and clay minerals form as a consequence of the action of liquid water. Now, I made the case yesterday that there has been a lot of water at the Opportunity landing site, and the rocks that we've been driving around or on show compelling evidence of the action of water. But when you look at the minerals that we've been driving around on, they are largely sulfate salts. And when you work through the chemistry, what that tells you is that the water that was involved in forming those rocks was very acidic. It had a pH of 3 or 2 or 1. So people run around saying, water on Mars, water on Mars. Well, what we've really found evidence for so far with Opportunity is evidence of sulfuric acid on Mars. And that's kind of nasty stuff if you're a microbe, okay, of most sorts. However, clay minerals like these, those form under neutral pH, under more normal watery conditions. And so what this evidence points to is rocks in the rim of this crater that are fundamentally different from anything we've seen before with this rover after over 7 years of driving around, and that point to conditions more suitable for life, possibly, than anything we have found so far. So here's the road ahead. Today, this is our position on day 2585 of the mission. This is the path going forwards. 4 kilometers to go, 3 kilometers to go, 2 kilometers to go, 1 kilometer to go, and then here's where we make our first landfall, if you will. The places that we're approaching, this large piece of the rim here is called, we've named it Cape York. This gap between it and the stuff to the south we've called Botany Bay. All of these are places that they're named after places that were discovered by James Cook on his expedition of circumnavigation in the ship Endeavour, which is what the crater is named after. So this is the path forward. We're doing, typically 100 to 150 meters per drive. And we drive typically 3 or 4 days a week. I'll leave it to you to do the math, but if the wheels don't fall off, we're going to get there. And it won't be too long. The view when we get there should be spectacular. This is a perspective view that shows the topography. The color code shows how steep the slopes are, and anything that's red would be very challenging for the rover. Anything that's black would be deadly for the rover. Here's Cape York. Here's Botany Bay. We're out here someplace. We pull up to this spot, and the view across this crater is going to be spectacular. I can't wait to see it. One of the things that we're debating is, do we spend a lot of time on Cape York, which is a little thing, or do we head south for these bigger things? This is a place called Cape Tribulation, and man, the view from the top of that would be fantastic. So we'll see. This is the view looking off in the distance. That's Cape Tribulation right here. Cape York is over that direction. So, like islands rising out of a sea of sand, these things are beckoning to us. And in the months ahead, if the rover survives, we'll get there. Okay, here's another prediction I'm fairly confident about, the Cassini mission. Cassini is a fantastic mission. It is an orbiter currently orbiting the planet Saturn. This is a beautiful picture of Saturn with the sun shining through the planet's rings. Recently, NASA has approved what they call the Cassini Solstice mission. This is a 7-year-long extension, and it essentially doubles the mission lifetime of the Cassini mission. Among the events that will take place during their extension is 54 more flybys of Titan. Titan is this enormous moon of Saturn. I'll be talking about it much more later on in the talk. It's got a dense atmosphere. It's got clouds. The only way you can really map the surface well is with radar. This will be 54 more opportunities to use radar to gaze through the clouds and map more of the surface. Another place that I'll be talking about later in the talk is Enceladus. Enceladus is a tiny little moon of Saturn. It's only 500 kilometers in diameter. It's bizarre to think that a moon that small would show geologic activity, yet there are literally geysers erupting from the south pole of Enceladus. And the Cassini spacecraft will fly by Enceladus 11 times, and on some of those, will actually fly through the plumes of stuff coming out of those geysers and make more measurements of what it's made of. So Cassini is going to continue and is going to continue to do great science. Messenger, this is a really exciting one. Messenger is a mission that just literally weeks ago was inserted into orbit around Mercury. Until Messenger's arrival at Mercury, the only spacecraft mission to Mercury had been flybys by the Mariner 10 spacecraft back in the mid-70s. Mercury's a tough place to get to. It's tough to get to because you have to go deep into the sun's gravity well. It's tough to get to because it's just hot there. You notice that the spacecraft is basically equipped with a giant parasol. Okay, this is a sunshade to keep it cool. Anyway, it has gone into orbit around Mercury, has just begun to turn on its instruments and start to map the planet. Let me just show you one very cool picture that came down fairly recently from Messenger. They're calling this a spider crater. Silly names like that are the ones that scientists make up to describe things when they don't actually understand them yet. But here's an impact crater, and then it's got this fantastic pattern of grooves radiating out from it. Now, what's going on here? Did the crater make the fractures? Or did the crater form and weaken the crust, and then later the fractures developed? Or were the fractures already there and the crater just luckily happened to land on top of it? Don't know. But this is just an example of the kind of really spectacular image data that's coming out of MESSENGER. It also has spectrometers, will map the surface, tell us what the planet's crust is made of. And we're looking forward to a long and successful orbiter mission around Mercury. Okay, so those are things that are currently in flight. Let me talk about one that hasn't launched yet but is getting close to it. This is an extremely ambitious mission called MSL, the Mars Science Laboratory. And this is another rover that will follow up to the discoveries made with Spirit and Opportunity. It has a fantastic new scientific payload. I'll tell you about that in a minute. And the way this thing lands is both fascinating and terrifying. It's shown up here at the upper left, and this is what's called a sky crane. If you were at my talk yesterday, I described how Spirit and Opportunity landed, and it was this terribly complicated scenario where we had airbags that would bounce on the surface and deflate, and then the lander would open up and turn itself right side up, and there were all these mechanical things, unfoldings that had to happen in order to make it work. And what I always wished was we could just take the rover and put it on the surface, you know, and not have to go through all that rigmarole. That's what this thing does, but it's a little scary. It comes in with a heat shield, just like Spirit and Opportunity, deploys a parachute, just like Spirit and Opportunity, and then what pops out of the aeroshell is this thing. And it's a two-part spacecraft. The top part that you see there is called the descent stage, and then here's the rover. And it flies like this. There's a cable, and it's called a sky crane because it is a crane, and there are rocket motors that are firing up here, and it's lowering this thing on a rope. And it flies down together, and if there's winds in the Martian atmosphere, it compensates for all those. And the wheels touch down, it senses touchdown, fires some explosive devices that cut the cables free. The descent stage flies away, and the rover's sitting there in the soil, 6 wheels in the dirt, ready to go, if it all works. We're all very excited and very nervous about this. The rover is big. It's about the size of a Mini Cooper. One of the things that you'll notice in this depiction of it is that there are no solar arrays. With Spirit and Opportunity, we are dependent on solar power for our electrical power, and we are dependent on lucky wind gusts to clean the solar arrays off. We want to keep getting power. This thing has a big lump of plutonium-238 on the back end of it. And that's what's called a radioisotope thermoelectric generator, and that provides a steady source of electrical power. Our rovers were designed to last for 90 days, and we're lucky that they've lasted 6 or 7 years. This thing is designed from the outset to last for years. It's big, as I said. The wheels are like this. It's a very large vehicle. It carries a very complicated, very sophisticated science payload. I won't take you through the whole payload. I'll just talk about this one instrument here. It's called SAM. Here it is. Just that instrument is almost as complicated as Spirit and Opportunity. It's a phenomenally complex instrument, and what it does is it is able to detect organic molecules at the parts per billion level in Martian samples. So we can reach out with this device here, drill into rocks, take that powdered rock sample, put it into this device, and search in ancient Martian rocks for the building blocks of life. It's going to be a very exciting mission. We don't know where we're going to land this thing yet. There are 4 candidate landing sites. All of them are very exciting. Here are 2 of them. One thing that characterizes all of those landing sites is that they all have clay minerals. They were chosen for that reason. This business of finding clays is terribly important. Now, Spirit and Opportunity were built by good friends and colleagues of mine, people who I respect and love and have worked with for years. Those same people are now building the MSL rover. And what I am determined to do is to get to the clay minerals at Endeavour before they get to the clay minerals at this site with that rover. I don't know if we'll make it or not, but we're going to try. Anyway, the landing sites are fantastic. Some of them have thick sequences of layered sediments. This is one that clearly has a delta deposit where water has flowed into a crater and deposited these deltaic sediments. This is going to be a fantastic mission, and it's one that we're all very excited about. New Horizons has launched, and it's on its way to Pluto. New Horizons is in the interesting scenario where its target was a planet when it launched, and by the time it gets there, it's not a planet anymore. I'm sure many of you are familiar with this debate over whether Pluto should be called a planet or not. I mean, the real answer is that Pluto is one of a family of many objects, and if Pluto should be considered a planet, then all of those other objects should be considered planets as well. So from a logical, scientific perspective, it sort of makes sense to not consider Pluto a planet. Personally, I'm a bit of a traditionalist. When I grew up, there were 9 planets, and I don't see why Pluto couldn't have just been kind of grandfathered in on a technicality. But anyway, that's where it stands. And it's going to fly by Pluto, and it's going to be very exciting. Okay, so those are some of the missions that are in the works. Now let's talk about what comes next. Imka mentioned that one of the things that I've spent the last couple of years working on is this thing we call a decadal survey. This is requested by NASA. It's carried out by the National Research Council. It involves inputs from hundreds and hundreds of planetary scientists across the country and overseas. People here at Berkeley were very much involved in it, as many other places. And it lays out a plan of exploration for the coming decade. In our case, it was for the decade from 2013 to 2022. So now what I'm going to do is I'm going to take you through some of the missions that were recommended by the Decadal Survey, both for the next decade and for the decade beyond that. So the crystal ball is getting a little cloudier here, but we're still kind of doing okay. Now, in the process of generating the recommendations, of recommending missions for the Decadal Survey, we studied a large number of planetary missions, 28 different missions we studied in detail. And this part of the job was one of my favorite parts of the whole thing. One of the things that I love about planetary missions is the part of the process I call the blank sheet of paper. When you've got literally a blank sheet of paper in front of you, an idea for something you want to fly, and you get together a bunch of smart people and you start to design a mission. And it's a fascinating, exhilarating, very complicated part of the job. And we sort of got to do the blank sheet of paper thing about 28 times over in the course of doing this study. And then, of course, once we'd studied those missions, we had to pick the few best ones to recommend. But here's just a list of the missions. And I'm not going to read all of these to you, but I'll go through a few of them. Mercury lander. Just what it sounds like. Follows on after Messenger and lands on Mercury. This Venus In Situ Explorer, that's a Venus lander. Venus Mobile Explorer, that's a lander that lands on Venus, takes off, and then goes and lands again. Lunar South Pole Aitken Basin Sample Return, there's a huge impact basin on the far side of the moon. Remember, all the Apollo landings were on the lunar near side because, the astronauts needed to talk to Earth. But on the other side of the moon, there's a huge impact basin that punched completely through the lunar crust and down into the lunar mantle. And so if you can go to the other side of the moon, land by that impact basin and get ejecta from that basin, you can get pieces of the lunar mantle. It's a way to actually get inside the moon, and then you bring those back. Bunch of Mars missions. I'll talk about several of these. Mars Sample Return is certainly the most complex and ambitious of all of them. Outer solar system, Europa. Europa is this moon of Jupiter that has a crust of ice and probably an ocean of liquid water under that ice. That makes it a tremendously important target. I'll talk about that mission in a lot more detail. Io. Io is another moon of Jupiter. It is the most geologically, most volcanically active body in the solar system. Saturn probe, this puts an entry probe into the atmosphere of Saturn. When Cassini went to Saturn, there was an orbiter and there was an atmospheric probe, but that atmospheric probe went into Titan. went into the atmosphere of Titan, one of the moons. We have never put anything into Saturn's atmosphere. And this one would fill the gap in that knowledge. Titan Lake Lander. It's a boat. There are lakes of liquid methane and ethane on Titan. And this would actually go sailing in one of those lakes. These are some cool ones. Uranus Orbiter, Neptune Orbiter, and probe missions. There are basically three kinds of planets in the solar system. There are the terrestrial planets, the rocky worlds, Mercury, Venus, Earth, Mars. We've done a lot with those. There are the gas giants, the two big gaseous planets made mostly of hydrogen and helium. That's Jupiter and Saturn. We've done the Galileo mission to Jupiter, the Cassini mission to Saturn. And then there are the ice giants, Uranus and Neptune, and they're made of very different stuff from any of those other planets. And in contrast to those other planets, all we've ever done at Uranus and Neptune is two flybys back with the Voyager 2 mission using early 70s technology. So there's enormous potential for new discoveries here. Then you get to the smaller bodies, return a sample from an asteroid, land on an asteroid. Very interesting object called Chiron. This is an object that's out between the orbit of Saturn and Uranus, nothing else like it in the solar system. Comet surface sample return. Return a sample from the surface of a comet nucleus. So 28 missions, great fun studying them. The hard part was picking the best from this set to recommend for flight. So let me talk to you now about some of the recommended missions. This is one. It's called a Mars Trace Gas Orbiter. Recently, there's been a very interesting discovery that's been made regarding the Martian atmosphere. It's shown in this picture here. These are mostly Earth-based observations, and what they have shown is evidence for methane in the atmosphere of Mars. Now, what's unusual about that is that if you ask yourself, how long will a methane molecule last in the Martian atmosphere? The answer is measured in years, or tens of years, or maybe like 100 years. It's very, very short. Those molecules don't last long because they're easily destroyed by ultraviolet radiation, and lots of ultraviolet radiation hits the top of the Martian atmosphere. So if we're really seeing methane in the atmosphere, what that says is that there is some active source of methane at or below the Martian surface. What makes methane? Cows make methane. It's probably not cows. Various forms of microbial life make methane. In fact, it's microbes inside the cows that make that methane. And then volcanoes can make methane as well. But what this says, this observation is saying that if this is correct, Mars is either volcanically or biologically active, or both. And so this is a mission with a spacecraft that would be built by the European Space Agency, with NASA providing most of the science payload and the launch, and it would follow up on these observations and try to identify the specific sources of methane and its detailed concentrations in the atmosphere. Beyond that, one of NASA's programs of planetary exploration is a program of missions. It's called the New Frontiers program. That mission to Pluto that I described is the first of the New Frontiers missions. And the way New Frontiers works is we recommend a small list, a short list of potential missions. And then groups of scientists get together, team up, write proposals for missions that can cost up to like $1 billion. And one of those missions gets selected from those proposals. So it's a competitive selection among a limited number of candidate missions. New Horizons, the Pluto mission is the first. There's a mission called Juno that's it's going to go to Jupiter. That's the second New Frontiers mission. There's a third one that's in the process of being selected right now. And we said, okay, NASA should pick 2 more New Frontiers missions, the 4th and the 5th one, in this coming decade. We recommended that the 4th one, so the next one selected in the coming decade, should be chosen from among these 5. Of all those mission candidates that I talked about, these were some of the ones that bubbled up to the top just based on their science return. Comet surface sample return. I'll show you this one in a little more detail in a moment. Returning samples from the surface of a comet. There's that lunar sample return mission from the lunar far side, getting inside the moon. The Saturn probe mission. Trojan Tour and Rendezvous, there are these objects called Trojan asteroids that are in the same orbit around the sun as Jupiter. They share Jupiter's orbit, and they're 60 degrees ahead of or 60 degrees behind Jupiter at that planet's Lagrange points, as they're known. And this is a mission that would go and explore those. And then here's that Venus lander mission. So what we recommend, these were the top 5. And we recommended that if none of these things have flown by the time NASA makes its selection, that the 4th New Frontiers mission, selected sometime, around 2015 or so, should be chosen from these 5. And we leave it up to the competition that will be held to decide which one will actually go, and the best mission wins. Then, another 5 or so years later, NASA should pick another one. And which one should they pick? It should be whatever is left over from those 5. And then we're going to throw 2 more into the mix. One is the Io mission. This is a mission that would orbit Jupiter and do many flybys of this violently active volcanic moon. And then a lunar geophysical network. Now you might say, well, wait a minute. We put a bunch of geophysical stations, seismometers, on the moon back on Apollo. Didn't we? Yeah, but again, all the Apollo landings were on the near side of the moon, which means that all of those seismometers are on the same side of the moon. That's not a good way to find out about the deep interior of the moon. You want to have them distributed over the lunar globe. And so this is a mission that would do that. So those are the recommended moderate cost missions. Now we get to the good stuff, the expensive ones. Oh, forgot about this one. Yeah, comets. I promised you I was going to tell you about one of these missions. This is what comet nuclei look like. Comet nuclei are they're tiny little things, a few kilometers in size. These are a couple that we have flown by. The thing that's great about comets is not just that they're photogenic, it's what they're made of. And here's a list of some of the constituent molecules of comets, the things that stream off of a comet when they get close to the sun. And you see things like water. Okay, that's interesting. We need water for life. We need water. Water is what makes up our oceans. Much of the water on Earth may have come from comets, but you also find things like methane. There's ethane up there. There's complex hydrocarbons, ammonia, cyanide. There's all sorts of interesting things in comets. The building blocks of life on Earth were probably in large measure delivered to Earth initially from comets. I mean, there are molecules in your body that got to Earth by being delivered from comets. And so this is a way to study our planet's building blocks and the building blocks of life. It's a complicated mission. This is what the spacecraft looks like. Comets go pretty far from the sun. And you want to actually encounter a comet when it's far from the sun, because when it's far from the sun is when it's cold, and that's when you don't have a lot of stuff streaming off of it. But when you go far from the sun, you need great big solar arrays for electrical power. This thing would hover above a comet nucleus, go down to the surface, and then use kind of a spinning brush to brush material off of the surface and suck it into a container. The container would then be launched on a trajectory that would ultimately bring it back to Earth. It's a complicated mission. Okay, now we get to the flagships, the really expensive missions. The highest priority flagship mission that we recommended for the coming decade is to begin the process of returning samples from Mars. We have gotten to the point now where our understanding of Mars is so good that we can identify the right places to go on the Martian surface to bring back the most interesting rocks. And despite the fact that we can build fantastic instruments and take them to the Martian surface with rovers like MSL, the best instrumentation is always going to be the stuff that's back on Earth, because when you get these rocks back to Earth and you can use very sophisticated analysis techniques, you can find out things about these rocks that you can never, ever hope to do on the planet's surface. So Mars sample return has sort of been the holy grail of Mars science for a very long time. And what this program does is it breaks the process of sample return down into 3 parts, 3 successive missions. And here's how the scenario goes. The first mission, which we recommend to fly in 2018, goes to the Martian surface with a rover, a little bigger than Spirit and Opportunity. That rover drives around an interesting site, selects samples, collects them, and places them into a container, a sample cache, which is then on the Martian surface. And that's all it does. They're going to come back eventually, but what that first mission does is simply collect the right samples. The second mission then sends another vehicle that lands close to that sample cache. A little rover goes over, gets the cache, brings it back, and sticks it into the nose cone of a little rocket, cranks it up to a vertical position, and shoots that sample cache contained in a spacecraft the size of a coconut into orbit around Mars. So now that coconut-sized spacecraft is orbiting Mars. Now, a third mission, stay with me on this. A third mission comes, and in the vastness of space around that Mars, finds that coconut, gathers it in, places it into a return capsule, and sends it on a trajectory back to Earth, where it lands in the desert of Utah with a thump about 25 years from now. And the samples come back to Earth. It's a hard thing to do, folks. The way you would land would be, again, using this terrifying sky crane system. This is the descent stage that's been developed for the Mars Science Laboratory. Now, this mission, when it was originally proposed to us on the Decadal survey, was a joint enterprise between NASA and ESA, the European Space Agency, that would actually land 2 rovers at the same site. One NASA rover, one ESA European rover. This is what the NASA rover would look like. It's got its name right now is MAX-C, which stands for Mars Astrobiology Explorer with Caching, I think. And it drives around, and it's got this fiendishly complicated thing on the front end of it that collects the samples and puts them in a cache. And that's the job of this rover. The European rover in the original concept was called ExoMars. And the highlight of ExoMars was that it carries a drill that is able to drill 1 to 2 meters down below the Martian surface and get samples from there. Very exciting pair of missions. What we found when we studied them together, however, was that flying 2 rovers was simply too expensive. The cost to NASA of flying these 2 rovers was going to be $3.5 billion, which was just too much. So what we recommended was that NASA and ESA work together to simplify that mission, and right now the 2 agencies are collaborating, trying to find a way to take those 2 rovers and combine them into just one and reduce the cost of the mission substantially. But the idea is that first mission creates a sample cache. Then here's the second mission. It too carries a little rover. This is called a fetch rover because its job is to go fetch the cache, brings it back, puts it into the nose of this rocket here called the Mars Ascent Vehicle, and that blasts that precious coconut into orbit. And here's the coconut collector mission. There's the sample cache right there orbiting Mars, and this orbiter goes and fetches it, catches it, puts it into this sample return canister, and sends it back to Earth. When it gets back to Earth, it goes into a sample receiving facility. This is what the sample return canister looks like, the thing that's going to come back to Earth. And if you look at that for a minute, you see the heat shield, you see the sample return canister, you see some cushioning material around it. You notice what's missing? There's no parachute. There's no parachute. Why isn't there a parachute? Well, the answer to that is that people, rightly so I think, are concerned that you don't want to inadvertently release Martian materials into the terrestrial environment. Now, not too many of us believe that there are, dangerous organisms that are going to be brought back from Mars and be inside this capsule, but you shouldn't be reckless about such things. And so you are required, quite sensibly, to build a capsule that is so rugged that even if no parachute deploys, when it hits the ground, it will not break, it will not fracture the samples, it will not release the samples. So if you got a sample container that's tough enough to not need a parachute, don't fly a parachute. So it actually doesn't have one. It lands pretty hard. But that's the idea. All right. This one's a real favorite of mine. Europa. Europa is, as I said, it's a moon of Jupiter. It's roughly the size of the Earth's moon. We know from its density that it must be made mostly of rock and metal, and yet its surface is made of ice. It's made primarily of water ice, and it is laced with this intricate, complex pattern of fractures that suggests that that icy shell has been deformed and fractured and cracked in various complex ways. If you ask yourself, what does Europa look like on the inside, there are both theoretical calculations and observations from the Galileo spacecraft that suggest very strongly that it looks something like this. You have a small metallic core, you have a big mantle, if you will, of rocky material, and then when you get close to the surface, here's that rocky material, there's the crust of ice, but both the calculations and the observations suggest that this icy crust is pretty thin, and beneath it lies an ocean of liquid water. And what that means, if it's true, is that there are two kind of accessible oceans in the solar system. We've got one, Europa's got the other. It's a tremendously exciting thing because, again, water is a necessity for life. Now, another necessity for life is some form of energy. So you might ask yourself, well, okay, sure, there's an ocean there, but if you want to have organisms live in that ocean, what are they going to live off of? What's their energy source? Ice is opaque enough that you can't expect sunlight to shine down through that stuff and have photosynthetic organisms living in that ocean. Okay, that's not going to work because this ice might be 10 kilometers thick or something like that. But, see this red stuff here? What that's representing is the idea that inside this rocky mantle, temperatures are high enough that you can get undersea volcanism, that you can get volcanic activity taking place on Europa's seafloor. And we know that on Earth's seafloor, volcanic activity and the hydrothermal vents that are associated with that support complex biological activity that is fundamentally energized, that derives its metabolic energy from the planet's internal geophysical heat. So Europa, and this environment right here, is one of the most compelling places in the solar system to look for evidence of life. Now, it's a hard thing to do. And we're not going to send a submarine the first time we go to Europa. We don't know how to do that. The big question is, how thick is the ice? Where are the thin spots? And so the idea is that you would fly a mission that would contain it would carry a number of instruments. One of the most exciting is a long wavelength radar. You know, the way we have mapped the thickness of the Greenland ice sheet, of the Antarctic ice sheet, and mapped the rock underneath is by using radar at long wavelengths that can see through kilometers of ice. Well, the same thing will work on Europa. And you can use that system to look through that ice, find the thin spots, find the place to go with a lander mission or with a submarine mission. So this is a very, very exciting mission. The cost estimates for this one came out very high. It came out at $4.7 billion, which was the number that broke my heart. And we're looking right now very hard at ways to make that less expensive, but still get the job done. Uranus and Neptune. Another one of our recommended missions is the Uranus Orbiter and Probe. This is like a Cassini mission or Galileo mission to Uranus. And it would go to Uranus, it would put an orbiter into orbit around the planet, multiple flybys of Uranus moons, good observations of the rings, and then a probe that would go into the planet's atmosphere. Now, why, you might ask, Uranus instead of Neptune? You know, either one would be great. They're both going to be fantastic. The reason that we recommended Uranus for the coming decade is that when you simply look at the spacecraft trajectories that are necessary to get from Earth to these planets, the spacecraft trajectories that go to Uranus in the next decade are just more favorable than the ones that go to Neptune. Also, Neptune requires some special technologies including one called aero capture, where basically you drag the spacecraft through the planet's atmosphere to slow it down, that Uranus does not, which makes Uranus easier to do. But either one of those, Uranus or Neptune, could be a fantastic mission for the decade to come or the one after that. Here's another good one, Enceladus. This is that crazy little icy moon of Saturn, 500 kilometers in diameter, tiny little thing. But there are these prominent fractures near the south pole of Titan, and erupting from those fractures are these plumes of material. And there's fantastic stuff in those plumes. The Cassini spacecraft has flown through those plumes and has measured the composition, and there's lots of water, but there's also methane, there's ammonia, there's CO2, there's complex organics, there's interesting stuff going on down inside of Enceladus. Now, Cassini flies through it occasionally, but the idea here would be to send an orbiter to Enceladus that could really study that moon in detail, that could do many, many flybys through the plume, that would have a very sophisticated payload that is specifically aimed at really studying those plumes and learning what they tell us about conditions down inside of Enceladus. Titan, fantastic place. Titan is roughly the size of the planet Mercury. It's a moon of Saturn. It's made mostly of ice, has a dense atmosphere. The atmosphere is made mostly of nitrogen, same thing that is the primary gas in the Earth's atmosphere. The atmospheric pressure at the surface of Titan is 50% higher than the atmospheric pressure on Earth. It's a dense atmosphere. It's got a cloud cover, a haze of hydrocarbon smog. There's methane in the atmosphere of Titan, and when you shine ultraviolet radiation on methane, again, what happens is the molecules break up. But on Titan, there's so much of it that they can recombine into more complex organics, and it makes this smog that obscures the surface. But when you use radar to look through that smog, you find this complicated icy surface, and then what you find is that Titan actually has a hydrological cycle. It rains on Titan. There are rivers. There are lakes. But the fluid in the rivers, the fluid in the lakes, the fluid in the rain is not water. It's liquid methane and ethane. And it produces these phenomenal features with dendritic valleys and just very familiar looking things, and yet the fluid is methane and ethane. So we looked at a mission that would study these in comprehensive detail. You can do some kind of cool things on Titan. You can put a little boat into the lake. You can fly a balloon in the atmosphere. You can fly an orbiter around the planet with radar, around the moon with radar. This mission costed out at $6.7 billion, which was even more expensive, but this is one that has great potential for the future. Now that was a mission that would try to do a comprehensive study of Titan, understand the hydrological cycle, understand the climate, understand the geophysics. A different approach is to say, look, this is a very complex, interesting object, but the most interesting thing is the lakes, so let's just go there. So this is a mission that we looked at that was just targeted at Titan's lakes, and you can see a radar picture that shows some of these lakes here. This picture, you got to sort of stare at this for a minute to realize what you're looking at. This is a picture of the spacecraft. And this image is taken from, I'll say, underwater, looking up at the surface. Now, it's not water, it's liquid methane. But here's the boat. The underside of the boat, you can see Saturn in the, hanging in the sky. But this is looking up at the underside of the boat, and here's the little submarine that it just dropped to go down to the bottom of the lake. And it consists of two pieces, one of which is heavy, dense, negatively buoyant, and the other is positively buoyant. And this thing has all sorts of cool stuff on it. My favorite instrument here is a rain gauge. That's not something you usually put on a spacecraft, but this would actually have a rain gauge on the boat to look at how much rain, methane rain, falls out of the sky of Titan. And this sort of shows the mission profile. This is a little bit hard to read, but basically what this thing does is the boat lands at the surface, and then it releases the submarine. The submarine is in two parts, and when those two parts are joined together, it's negatively buoyant. In other words, it sinks. And it drops slowly to the bottom, and it sits there for a while, making measurements at the bottom of a methane lake on Titan. Makes its measurements for a while, and then once it's done, it fires a little explosive squib right here that cuts the top part free from the bottom part. The top part is positively buoyant. It floats. And so now it drifts back up to the surface, comes up to the surface, and transmits its data to a spacecraft orbiting Titan, which then relays it back to Earth. If you don't think this is cool, I don't know what to do. What I just described to you is probably a good, easily 25 or 30 years worth of planetary exploration. It's expensive stuff. We've worked very hard to come up with realistic cost estimates for these missions. The missions that are expensive, we are working really hard to bring the costs of those down. But carrying out these missions will require significant funding. And the funding needs to stay steady or go up a little bit going forward to kind of do the program that I've laid out for you. Now, in recent months, we have received from the Obama administration projections going forward for funding for planetary exploration in the United States for the next 5 years. The funding that's recommended for fiscal year 2012, here's the number for 2010, $1.3 billion. For 2012, it's $1.488 billion. That's a good number. That's a number that's consistent with the plan that I laid out for you. That's a number that will allow us to do these exciting missions going forward. But then it falls off a cliff. The projected numbers from the Obama administration go 1.36, 1.32, 1.27, 1.18 in fiscal year 2016. And this does not account for inflation, so it's actually worse than this. The buying power is going down even more sharply than what I've described here. Now, these are, the word that they use in Washington, D.C. to describe this budget is notional. I find that an amusing word. But the idea is, this is a real number. Everything else is a shot across our bow. It's telling us that this is what we, the administration, intend to carry out. Now, of course, the budget has to actually be enacted by the Congress and is signed into law by the president. And there are some in Congress who look at this and see the demise of planetary exploration in the United States. If this budget happens, then the inexpensive missions that I mentioned, like the New Frontiers missions that I talked about, those we can still afford. But the flagship missions, sample return, Europa, Uranus, none of that can happen. The multi-billion dollar, even the $1 billion, $2 billion class missions, they go away. The United States can't do them anymore. Now, this is what the Obama administration has proposed. Congress has to act on this. The people in Congress are our elected representatives, and if you feel strongly that we should be continuing to do a program of robotic planetary exploration that keeps this country at the forefront of that field, with samples coming back from Mars and orbiters to Europa, now would not be a bad time to let your congressional representatives know that a budget like this is one that's going to take us out of that business. I, however, remain optimistic. I believe that ultimately we are going to do missions of the sort that I just described, and that when you look in the decades down beyond that, here's where I'm waving my arms and speculating, that even better things await. So let me just describe for you a few kind of really longer-term things that I'd love to see happen. One of them is returning samples from Enceladus. I mentioned that mission that would fly through the plumes. Here's one where you produce a collector. This is a material that you can put out in the breeze, and you can fly through one of these plumes. The plume particles impact it, they get decelerated by this collector, and then you send the whole thing back to Earth. You don't actually have to land on Enceladus, you just collect the material. That would be a fantastic mission. Another one, obviously, is humans to Mars. Now, sending humans to Mars has been 30 years in the future for the last 30 years, so it's going to be at least 30 years before this happens. But despite the fact that you can do marvelous things with robotic explorers on the Martian surface, the best exploration, and I believe the most inspiring exploration as well, is ultimately going to be done by humans. And I think sending humans to Mars is something that should and will lie in our future. And I think personally that Mars is a much better target for human exploration than the moon or asteroids, because frankly, the moon or asteroids you can do pretty well with robots. Mars is so complicated that humans can really contribute there. I'm not sure if they would want to drive around in something that looks like this, but they can do a good job. Finally, this is one of my real favorites. You know, I've often said that if I could figure out how to do submarines on Europa, I wouldn't be messing around with rovers on Mars. This is a fiendishly complex mission. You need to go deep into Jupiter's gravity well and land on the surface of Europa. Europa lies deep in Jupiter's magnetic field, and so your spacecraft is subjected to punishing charged particle radiation. Somehow then you have to drill or melt your way down through maybe, 10 kilometers of ice, and then release into this water column, which might be 100 kilometers deep, a free-swimming autonomous vehicle that's able to somehow navigate its way down to the bottom of the ocean, find whatever interesting stuff lies there, collect data about it, and then somehow get that information back, transmitting it to this thing, which transmits it to the surface, which transmits it to an orbiter, which transmits it to Earth. I want to see this mission happen. I'm trying to get lots of exercise, eat healthy foods. I'm going to have to live a long time to see this mission happen, but I truly hope that it will. The big question, of course, then, is what will all of these missions discover? My answer is, I don't know. You got to ask this guy. Thank you very much.
First thing I wanted to ask about is the sample return mission.
From Mars.
Why is it still being considered to do the analysis on Earth rather than at the space station, given the possibility of contamination?
Bunch of reasons for that. I think probably the most important one is that we really do know how to deal with the contamination problem. The contamination problem is very similar to ones that face people working with various disease agents and that sort of thing. There are facilities that can contain such things, so it's a tractable problem. You can put much, much, much better instrumentation into laboratories on Earth than you can put into the space station. And it just sort of puts off the problem. I mean, if you contaminate the space station, then what do you do? So doing it on Earth is the sensible place, I think.
And I've read that it's thought that there may be a liquid ocean underneath ice crusts on Ganymede and Enceladus, as well as
Enceladus and Ganymede both possibly. I think Enceladus, it's more likely just sort of little liquid zones. Ganymede quite possibly, but the reason that Europa is more attractive than Ganymede is that on Ganymede that ice crust is really, really, really thick. It's much more accessible in Europa.
That's what I thought.
Yeah.
Thank you.
Sure. Hi.
One of the problems of prolonged space travel for humans is that it's detrimental to their bodies.
Yes, it is.
And I wish you could talk a little bit about that
Sure.
in terms of
Sure.
travel.
Space flight is tough on human bodies in several ways. One is that long-term exposure to microgravity results in redistribution of a variety of fluids and electrolytes in your body, and one of the consequences of that is bone decalcification. A lot of the work that's going on the space station right now is to develop countermeasures for that, and those are moderately effective. So I think it takes 7 months to get to Mars. We can probably solve that problem. Another serious problem is radiation. And solar flares can produce intense radiation bursts that could be very detrimental to human health. both on their way to Mars and on the Martian surface. The way to deal with that is shielding. You just need a lot of mass between you and the sun. The thing about these solar flares is you can sort of see them coming. The particle fluxes don't travel at the speed of light. You find out that this thing is coming, and as long as the astronauts have some place to go hide, they're going to be okay. The way you hide on a spacecraft on the way to Mars is that you carry with you some significant mass that you use for shielding. That you would take mass that's good for something else too, like water or something, and then you have a little small place where you can go to keep yourself safe until the flare is over. On the Martian surface, it gets a little easier because basically what you do is you build a storm cellar. Okay, you dig a hole beneath the Martian surface, and as long as you're, a meter or two down, you're going to be okay when a solar flare happens. But it is a serious problem and one that could be very detrimental to astronaut health unless the appropriate shielding is available.
Hi, you mentioned a lot of exploration on Mars,
Yeah.
Specifically towards craters. Why are you looking only at craters? Like, why is that a big deal?
Yeah, the reason that we focus so much on the impact craters with the rover Opportunity, the reason for that is simple. The rocks that we've been driving around on for the last 7 years are sedimentary rocks, and they're a bunch of horizontal layers, okay? And they're very flat-lying, and the surface itself is very flat too. So as you're driving along that surface, you're basically just seeing the same rocks over and over and over again. What you want to do is have the capability to get down below the surface. Now, we don't have a drill. Okay, we didn't bring a backhoe. We have no way of digging a hole. But what we can do is rely on the holes that nature has dug for us in the form of impact craters. So the beauty of these impact craters is that they provide access to other layers in that stack of sediments, each of which represent a different page in the Martian history book. And so we're able to study those other rocks by going to craters. That's the reason we do it.
Great, thank you.
Sure. Hi.
I have a question about there's some limited private funds going into space exploration. Do you think that will affect the economy of space exploration in a longer term, or is it just a marketing thing?
The money the private funding that's being invested in space right now is almost all money that is intended to return a profit to the investors. There are a couple examples. One is Virgin Galactic. And they have built a spacecraft that will be able to take passengers on, it's not orbiting the Earth, it's just a ballistic trajectory where you have maybe 15 minutes of zero gravity going over the top, but you get to the fringes of space and back again. And people can pay, I forget what the going price is, that's $4,000 or $10,000 to go on that ride. And the company makes money. Another great example is SpaceX. This is a company I have a lot of enthusiasm and respect for. And this is a company, it's a privately owned company, started by Elon Musk, the same guy who started PayPal. And they are developing rockets called the Falcon family of rockets, Falcon 9 and Falcon Heavy, that they hope, and I hope, will be able to deliver payloads to Earth orbit for paying customers at a much lower cost than we typically now spend for our Delta rockets and our Atlas rockets from some of the more traditional aerospace companies. So we are now beginning to see private enterprise really start to be major players in the space business, but all of the examples that I know of rely on a sound business model that has paying customers lined up and ready to pay real money for those services. Finding people who are willing to pay lots of money for data from Uranus, rocks from Mars, that's a little tougher. So there are some things that I think for the foreseeable future, we have to rely on the government to take care of.
Well, thank you all for coming.
Thank you.
And Steve, thanks for an exciting talk again.